All right, so in this video, we're going to go over section 3.3, which is derivatives of products and quotients. So if you remember in section 2.5, we found that the derivative of a sum is the sum of its derivatives. And the question we're asking here is the derivative of a product the product of the derivatives? Well, by doing the four-step process and finding the limit of the difference quotient that we saw before, we see that the answer to this is no. And let's look at an example here. So let's say we have two functions. F of x is equal to x, and g of x is equal to x. And the product of these two functions is equal to x times x, which is equal to x squared. So we want to see if the derivative of a product is the product of the derivatives, meaning is the derivative of x times x with respect to x equal to the derivative of x times the derivative of x. And we know that the derivative of x with respect to x is just 1. So we get 1 times, again, 1. And so we get that the derivative of this is 1. However, we know that the derivative of x times x with respect to x is the same thing as the derivative of x squared with respect to x. And we know that we can use the product rule for this. So the 2 comes down in front, and then we have x to the power 2 minus 1, so x just to the power 1, and we get 2x. And we know that the derivative of x squared is 2x. And these guys here are not equal. So if we have two functions, f and g, this tells us, let's write it here, that the derivative of the product of these two functions is not going to be equal to the product of their derivatives. All right. So that brings us to the product rule. So if we're given two functions here, f of x and s of x, and if both of their derivatives exist, then the derivative of our original function is going to be our f of x times the derivative of our s of x plus our s of x times the derivative of our f of x. And then this is just given in different notation, right? So we could have s prime and f prime representing the derivatives. Same with the derivative of s with respect to x and the derivative of f with respect to x. All right, so let's look at this example here. So we're given this function f of x here, and we want to use two different methods to find f prime of x. So the first thing that we could do is we can distribute this 3x cubed to every term here. So this will be our first method for determining our f prime of x. So by distributing the 3x cubed, we'll get 6x to the 5th power minus 9x to the 4 plus 3x cubed. So then finding the derivative of this is pretty simple. We're just going to use our power rule. So we have 6 out in front and our constant multiple rule times 5, and then we have x to the 5 minus 1, so x to the 4, minus 9 times 4, x cubed, plus 3 times 3, x squared. So we end up with 30x to the 4th minus 36x cubed plus 9x squared. All right, so that is one way we can find the derivative of this function. Another way is to use our power rule. So here we have two functions. So let's do some color coding. We have f of x here and s of x here. So in the case of our example here, our f of x is this guy, and our s of x is this guy here. So using the power rule, first we'll have our original f of x, so 3x cubed, and we're going to multiply that by the derivative of our s of x. So I'll just write that in this notation. And then we're adding our s of x and multiplying that by the derivative of our capital F of x. All right. So we have this 3x cubed on the outside, and then we're going to take the derivative of this guy here. So we get 4x minus 3. And then we're adding, we have our 2x squared here. And then we're going to take the derivative of 3x cubed. So that's just going to be 9x squared. All right. Then multiplying, so expanding these terms, we'll get 12x to the 4 minus 9x cubed plus we have 2x squared times 9x squared, so we have 18x to the 4 minus 27x cubed plus 9x squared. And then combining like terms, we have 30x to the 4 minus 36x cubed plus 9x squared. All right, so we see that at the end, we get the same answer because these are two different methods for finding the same thing, for finding the derivative of our original function. So sometimes we can use either method, like in this case. However, sometimes if we have more complicated functions that we're multiplying, we will need to use the product rule. Additionally, on the exams, if the problem asks you to use the product rule, that's what we'll have to use. All right. Let's look at this example here. We have this given function, and we want to find the equation of the tangent line to the graph at x equals 3. So we know that if we're going to find the equation of the tangent line, we're going to have to find the derivative of our function. And we're given this here, and this is we could FOIL these guys out, but the process of doing that and then using the power rule to find the derivative is going to take a good amount of time. So here we're just going to use our product rule. So this is our first function, and it's multiplying our second one. So the derivative of this is going to be our first function, so 2x minus 9, times the derivative of our second function. So the derivative of this, we just bring the 2 down in front. So we have 2x, and then the derivative of 6 is just 0. And then we're going to add our second term, which is this second function here, times the derivative of our first function. So we have 2x minus 9, so that's just going to be 2. All right. So then we'll get 4x squared minus 18x plus 2x squared plus 12. And this leaves us with 6x squared minus 18x plus 12. All right, but our question did ask to find the equation of the tangent line to the graph at x equals 3. So we know that we're going to have to plug 3 in to our derivative here. All right, so we'll get 54 minus 54 plus 12. So this tells us that the slope of our tangent line at x is equal to 3 is equal to 12. Now we do want to find the equation of the tangent line. All we've found so far is the slope at this point. So what we're going to do is use point slope form. So we need to find another point. And we're given x is equal to 3, so let's look at what we get when we plug 3 into our original equation. All right, so this should give us, we have negative 3, and then we'll have 15 on this side. And so we'll get negative 45. All right, now I'm running out of room here. Let's move this guy up here. And so using point slope form, we can plug in what we know. So remember, point slope form, I'll write it up here, is y minus y1 is equal to n times x minus x1. So we have y, and we're going to subtract our y1, and we found that that is negative 45. Then we're going to plug in our slope, which we know is 12. And then we have x minus our x1, which is going to be 3. All right. And then solving for y, we get y is equal to all right. And then distributing this 12 here, we get 12x minus 36 minus 45. So we'll get minus 81. All right, so this will be our tangent line at the point x is equal to 3. Now for part B, we want to find the values of x where the tangent line is horizontal. So when the tangent line is horizontal, we know that our slope is equal to 0. So what we're going to do is find when our derivative is equal to 0. So we have setting that equal to 0. We can pull out a 6 from every term here. And then factoring this guy, we get x minus 1 times x minus 2. And so this tells us that the tangent line is horizontal for values of x equal to 1 and x equal to 2. All right. Now we're going to want to find f prime of x, for f of x is equal to 5x to the 8th power times e to the x, and f of x is equal to x to the 7th times ln x. So here we're going to use our product rule. We have two functions here, 5x to the 8th power and e to the x. So our product rule says we're going to take our first function, so 5x to the 8th, times the derivative of our second function. And we know from last video that the derivative of e to the x is just e to the x. Then we're going to add our second function times the derivative of our first. So we'll have 5 times 8, x to the 7th. So then we get 5x to the 8 times e to the x, plus we have 5 times 7, 5 times 8, so we get 40x to the 7 times e to the x. And so that is our derivative for this guy. And then for b, again doing product rule, we're going to do x to the 7 times derivative of ln x, and we know from our last video that's 1 over x. And then we're going to add our second function times the derivative of our first. And so we know that's going to be 7x to the 6. And so simplifying this a little bit, we're going to get x to the 7 over x plus 7x to the 6 times ln x. And then these guys will cancel, so we'll get x to the 6 plus 7x to the 6 times ln x. All right, and then we can pull out this x to the 6 if we want. We get 1 plus 7 ln x. All right, now we're going to look at derivatives of quotients. So similarly to the product of two functions, or the derivative of the product of two functions, the derivative of a quotient of two functions is not going to be the quotient of the derivatives of the two functions. So we have our quotient rule here. So if we have some function that's given by one function divided by another, and the derivatives of these two functions exist, then this is going to be the derivative of our function. So we'll have our function down here times the derivative of the top one, and taking out the original top function times the derivative of the bottom one, all over the bottom function squared. So something that really helped me when I was taking calculus is this little, I wouldn't really call it a mnemonic device, but it's very catchy, so it's easy to remember. So if I call the top function high and the bottom function low, what I remember it as is low d high minus high d low, all over low times low, or low squared. So that's just always how I've remembered the quotient rule. When I say low, I mean the bottom function, and then the derivative of the high function, so derivative of t prime x minus t of x times the derivative of the bottom function. And then we're squaring the bottom function. So if that helps you, great. If it doesn't, no worries. Okay, so let's look at this first example. We have our function f of x is equal to 2x over x squared plus 3. And so using our quotient rule, we have the bottom function, so low, times the derivative of the top, so 2. And I'll keep color coding these actually. Times d high, then we have minus high times the derivative of the low, so 2x. And this is all over low, low. All right, and we can simplify this a little bit. So distributing this 2 to both terms here, we'll get 2x squared plus 6, and then we have a minus 4x squared here, all over low, low, so x squared plus 3, and we can square that. And then last step, we will combine like terms, so we have a negative 2x squared plus 6, all over x squared plus 3 squared. All right, so not too bad if you follow this formula for our quotient rule. Now for b, we're going to do the same thing, keeping notation consistent. We're looking for y prime. So let's color code this again. We have our top function and our bottom function here. So we're going to do t squared minus 4, so low, times the derivative of our high function. So it's 3t squared minus 3. Taking out our top function times the derivative of our bottom function. Oh. So we just get 2t. And then again, this is all over our bottom function squared. All right. So then we're going to get 3t to the power 4 minus 3t squared minus 12t squared plus 12. All right, then we're taking out our 2t to the power 4 minus 6t squared. All right, and that's all over t squared minus 4 squared. All right, then combining like terms, we have a 3t to the power 4 minus 2t to the power 4 minus 3t squared minus 12t squared minus 6t squared. All right, so then we're going to get t to the 4 minus 15t squared plus 6t squared plus 12 all over t squared minus 4 squared. And then combining again, we'll get t to the 4 minus 9t squared plus 12 all over t squared minus 4 squared. All right, so that's our derivative for example B. And something to note here, if we look at this function, and let's say we were to swap these guys. So let's say our function was x squared plus 3 over, what was it, 2x. What we can do is rewrite this, right, as x squared plus 3 times 1 over 2x, which can be rewritten as x squared plus 3 times 2x to the negative 1. Now in this case, we could easily just rewrite our function like this and then use the product rule. So either way will work and give us the same answer. All right, let's look at a few more examples. So for A, find f prime of x. So we're going to use our quotient rule again. So we're going to have our bottom function, ex plus 2, times the derivative of our top function, so 3x squared, minus our top function times the derivative of our bottom function. And we know the derivative of e to the x is just e to the x, and the derivative of 2 is just 0. That'll be all over e to the x plus 2 squared. And then simplifying, we'll get 3x squared times e to the x plus 6x squared minus x cubed times e to the x. All right, and that's all over e to the x plus 2 squared. And then last step, I'll take out an x squared from each term. And then we can leave our answer as this. So we have, that would be our derivative for our example A. Now looking at B, we're going to do the same thing using our quotient rule. So we have low 1 plus ln x times d high, so the derivative of 4x is just 4, minus high, so 4x, times d low, so the derivative of 1 plus ln x. And we know the derivative of 1 is just 0, and then the derivative of ln x is 1 over x. And this will all be over 1 plus ln x squared. All right, and then simplifying this, we'll get 4 plus 4 ln x minus, these x's will cancel, so just minus 4. And then these 4's will cancel, so we're just left with 4 ln x over 1 plus ln x squared. And that is our derivative for that guy. All right, so the last thing we'll look at is an example in sales analysis. So we're told that the total sales, S, in thousands of games of a video game T months after the game is introduced is given by this function here. And the first thing we want to do is find the derivative of this function. And so we have one function divided by another, so we'll use our quotient rule. So we have low, so t plus 3 times the derivative of our 150t. So that's just going to be 150 minus 150t times the derivative of t plus 3. And so we know that the derivative of 3 is 0 and the derivative of t is going to be 1. And that'll be all over t plus 3 squared. And then simplifying this, we'll get 150 times t plus 450 minus 150 times t all over t plus 3 squared. And so we have 150t minus 150t, so we get 450 over t plus 3 squared. All right. Then for part B, we want to find s of 12 and s prime of 12 and interpret what these mean. So s of 12, we're just going to plug 12 into this guy here. And so we'll get 1800 over 15, which is 120. So what this means is, if we're looking at S as total sales in thousands of games, then this means, here I'll write this out. This tells us that the total sales after 12 months is, and it's going to be 120,000 because we're told S is the total sales after a certain amount of months in thousands of games. So since we got 120, it'll be 120,000, 120,000. All right, and then we want to find S prime of 12. So we're going to plug 12 into our derivative. So we get 450 divided by 12 plus 3 squared. So we'll get 450 divided by 225, and then we get 2. And so our derivative, we know that this represents the change, or the rate of change, right? And we're looking at the change in sales, since S represents the number of sales in thousands of games. So this tells us that the sales is increasing at a rate of, it'll be 2,000 games per month. All right. And then part C asks us to use these results to estimate the total sales after 13 months. So we just found that at 12 months, there were 120,000 games sold. And then we know that at 13 months, it will have increased by 2,000 games, since we're increasing by 2,000 per month. So it's going to be 120,000 games plus 2,000 games. And so we'll see roughly 122,000 games sold after 13 months. All right, so that's it for this video.